My name is Rong. I'm from University of Michigan School of Information. I'm glad to be here today to present our work on using neural network and user interface design to support interactive programming experience. This is a joint work with my colleagues Shiyan, Steve, Mira, and Eytan. So, our work is motivated by the fact that programming is not so easy. So there are many reasons for this, but two of the reasons that really drive us to do this work is that one, programming often involves a lot of API functions that are, involve a lot of complexities that can make it really hard for especially novice users to navigate through. And the second reason is that the user does not always know how to translate a task in their mind into the actual code they can write in the code editor. So in this work, we aim to find innovative solutions to support, a better programming experience. And among many types of many different types of programming types, we focus on interactive programming, which is the type of programming that you do when you interact with IPython notebook or R or MATLAB, where you enter a piece of code and then you execute. You can immediately preview the results and then you go back and iterate the code so that you can quickly get insights on the data, statistics, or generate visualizations efficiently. So let me show you what we built. Before I start the video, I just want to mention two things. So first, we implement our system for Python and one specific library, which is matplotlib. It is a very popular plotting library that can be used to generate statistical charts out of data. And the second thing is that in the video, we want to assume that the user will create a bar chart like this. This is something the user has in mind. And notice that the bars are red and there is a title above the chart. So let me start the video. Okay, so this is the interface of our system. On the left, you see a code editor, and top right is a query box, and the major part of the right section is multifunction display. So the first task, suppose the user wants to create a bar chart from scratch. So the user can just type in a query, create a bar chart, and as you can see, as the user types the query, the system automatically runs the functions that are related to the completing task. In this case, probably you cannot see clearly, but BAR, the bar function, is ranked the highest, and the color encodes the likelihood. So a list of images are displayed at the bottom, and these images are generated by the code examples that include the function. As you can see, the user can click on the image, and the code example that generates the image is automatically populated into the code editor, and the corresponding image preview is also displayed at the bottom. So that's task one. And now let's move on to task two. Suppose the user wants to add a title to the bar chart. Again, the user can type in a natural language query in the query box, add a title. And in this case, the system, again, automatically ranks the function that are most likely to complete the user's task, which in this case is title. And the user can click on the function and then click on the suggested parameter and then click on the suggested value and click insert, and the system will figure out where that line of code should be inserted into into this code snippet. And as you can see, after executing the code, title is automatically added to the chart. So that's task two. Now let's look at the next task where we suppose the user wants to modify this chart by changing the colors of the bar. So again, the user can type in a natural language query, change the color of the bar. And this time, since this is not inserting a new line but modifying an existing line, you can see that the system automatically highlights a line of code that should be changed. In this case, it's the line number 4. The user can click on the highlighted line, and now the system can use this context information to give the corresponding suggested parameter to change. The user can click on the suggested parameter and then suggested value and then hit update. And you can see that the code is automatically changed, and you can automatically see the preview. So that's pretty much what's in the video. Let's go back to the presentation. Okay, so let's do a quick recap of what we have seen in the video. So there are 3 scenarios. The first scenario is that the user created something from scratch. And the second and third scenarios are more subtle. It uses nuanced context information in the code, and where the user modifies an existing code snippet by either inserting a new line of code or changing an existing line of code. And we think that a lot of existing solutions are only targeting or mostly targeting on the first scenario, which is using some black box to convert a natural language to some kind of code example. And these existing solutions include Google or Stack Overflow. And in the software engineering community, a lot of people work on how to build better code search engines, or like so-called programming by example. And in machine learning and natural language processing communities, people work on so-called natural language-based code synthesis. And in our work, we have a heavier focus on the second and third scenarios, which is modifying existing piece of code based on users' natural language intention. And we think that a good way to build or implement these black boxes is to use deep learning. And deep learning has a lot of good benefits, like it is simple to use or keeps human out of the engineering loop mostly. It has good capability of doing transfer learning, and what's most important is that usually once you give it, the more data you give to a deep learning model, the better performance it can get. You can get out of the model. And very likely we have a lot of data for training such kind of models. In specific, we have a lot of code data, we have a lot of text data, and code text association data. These include Stack Overflow, GitHub, tutorials, textbooks, and so on. So how does this actually work? Well, any work about deep learning is actually designing a black box where you specify the input, specify the output, and finding the training data. In our case, we can easily specify the input and output of this black box. The input is natural language command and the code context, and the output is code suggestion. So what are the training data? Well, it is, we can provide the training data as a lot of natural language text, a lot of code examples, and natural language code association. So to actually get these training data, we actually went out to crawl this information from the web. We ended up with 50,000 code examples and around 90 million words in natural language corpus. So now it's time to go into the black box and see what is inside. So let's open this black box. And this is what it looks like inside. We call this a bimodal embedding model. Bimodal in the sense that its input accepts 2 modalities. One is code context and one is natural language. And to understand how this model works, we need to address 3 important problems. The first one is how to map a raw piece of code into this lookup table. At the bar in the black box, you see here, this is a lookup table or a dictionary with entries being code elements, which I will explain in the next slide. And the second problem is that how to map a natural language query into this natural language lookup table or a dictionary where the entries are words. And third important problem is how to map the model's output or model suggestion to user interface appropriately. So let's look at these problems one by one. So let's first look at the first problem, how to map a raw piece of code to the model, a neural network model. And here's our solution. So given the piece of source code, it always has some kind of tree structure. So we want to flatten out this tree by traversing from the root to all the leaf nodes and get some kind of flattened, the so-called code engram representation. For example, this source code has a function called plt.py, and it has a lot of parameters. So we can flatten it out by getting plt.py means the function itself, plt.py at 0 means the non-named argument, and plt.py at explode, which is the named argument, and so on. And it can get a lot more complicated than this, which you can refer to in the paper. So let's look at the second problem, how to map a natural language query to neural network lookup table. And our solution is this. So this is actually much easier than mapping source code, because in natural language processing and data mining, there's a well-known concept of bag of word model, where you can simply break up this sentence into a list of words, and then you map them to entries in this natural language dictionary, and naturally they fit in this bimodal embedding model's input. But there's a challenge though, because during training we don't have natural language descriptions given any piece of code. So what we need to do is to use API documentation as a bridge to find the natural language descriptions of any code elements that we want to we care about. That way we can generate simulated natural language queries as a surrogate in training. And during testing, very naturally, there is a user there to help us generate natural language queries, which can be naturally mapped to that bimodal embedding model's input. Okay, let's look at the third problem, which is mapping a neural network's output to a user interface. And what is the model's output? Well, the model outputs a distribution over all possible code engram representations. One code engram representation is like this, and there are a lot of these. So our question is, how do we map these to a user interface? Well, we get inspiration from this so-called spotlight search. If you have a Mac computer, you will be probably familiar with this user interface where you can enter a query and more than one items may be lightened up. So we think this is a clever solution to deal with ambiguities with queries, because when there are like multiple items associated with a query, the user can see what these options are, and also the user can also see all the other available options at the same time. So we want to adapt this to our problem, but there is still another challenge, because there are tens of thousands of entries in this lookup table, which is the model's output. We cannot afford to display tens of thousands of items here. So the solution is to leverage the hierarchy, or so-called the hierarchical structure in this lookup table, where there are functions and parameters and values. So based on this fact, we created something so-called nested layer spotlight search, where the user always starts from the top layer, which are functions, and then they can go down layer by layer. The next layer is parameters, and then values. So when the user makes a change on the lower layer, and the changes are back propagated to upper layers, and so on. Okay, so we have described model and the user interface. How well does this whole thing work? Well, we want to test this by using two experiments. The first experiment, we want to test how well does the model itself work. And the second experiment, we want to test how well does the end-to-end system work. In the first experiment, we test how well does the model work. We want to actually measure, can the model always rank the best suggestions highest? We do this way. We wrote code snippets that with slight variations so that they generate images with small changes. And then we ask crowd workers to describe the change between these two images. And we get a lot of descriptions or queries like these, like change the color of the bar. So in the end, we ended up with 361 queries collected for 5 such kind of image pairs. And then what we did was to give the source code that generates image A to the model, and then also give the query to the model and see if the model can predict what change is needed to make source code that generates image A to source code that generates image B. To give you an idea of what the model's output is like, here's an example. So suppose the input query is change the color of the bar, and the ground truth is plt.bar add color. That means the color parameter of the function plt.bar. And the output is a ranked list of code engrams like this. What we did was to take the ground truth and see how high it is ranked in the model's output. And in this case, it's the third one. So we do this aggregately and see on average what is the, where is the best result ranked at. And here is the experiment result. So the most prominent result is that based on mean reciprocal rank, on average, the expected result is ranked on the 4th place, which is the inverse of this number. And the other takeaway is that if you take away natural language context, you get a lower performance. Or if you take code context, you also get a lower performance. So in the next experiment, we want to test how well does this whole system work end to end. And we designed a lab user study to help us test this. What we did was to give the user a code snippet that generates an image that we call starting point image. And we also give the user an ending point image and ask the user to figure out how to change that code snippet to a different code snippet that generates that ending point image. And of course, using the system we provide to the user. So, of course, we have control group and treatment group. In treatment group or condition 1, the user can use information from CodeMend results or Google. And in condition 2, which is the control group, the user can only use Google information, Google results. So to give you an idea of what the interface looks like in the experiment, on the left you see that this is CodeMend result, and this is Google search result. On the right, which is the control group, this is the user only has access to Google search results. And here is the result of the experiment. We recruited 20 participants, and on average, the group with CodeMend plus Google completes a task using 108 seconds, and the group that uses Google only completes a task using 134 seconds. Although due to the large variance of task completion time within each group, the results was not statistically significant, we still think that this overall trend it was in a promising direction. And in addition, in the post-study survey, 70% of the users agree with the statement that CodeMend efficiently helps them solve their assigned tasks. And in the follow-up open interview, a typical response of the user provided by the user is that they really like, the system's capability of supporting free navigation through the functions and parameter space of a given API library. So the current system is still limited in many ways, and some future directions for this work is that how to identify usability issues to support a wider range of APIs, and how to find a better representation that can encode the hierarchical dependencies in code or natural language, and also how to find a better way to extract information from noisy web pages to support gathering a larger training data set. And lastly, how to directly encode the API knowledge into a deep learning model. So in summary, we have presented a neural network model that can improve the user experience of interactive programming. And we have shown that by using data from the web, we can train such model to predict, to generate relatively accurate suggestions. And lastly, we have designed a novel user interface that can support improving the productivity of user completing tasks using the output of the model. That's all, thank you. And the code and data are open source on the web. Thanks.
Thanks, Shiyan. We have time for a few questions.
Thanks. Mike Terry at Google. Really neat stuff. So with the training corpus, was that just matplotlib code and documentation?
Well, it is actually more than that. So we, like I said, we have 3 types of training data, a lot of text, and that text can be not only about matplotlib, but can be also about Python or programming in general, because deep learning has this capability of transferring data in a general domain to a specific task. And also code examples, mostly about matplotlib, and code text association is only the matplotlib API library.
So yeah, I guess my question is is your training data mostly biased towards matplotlib, such that if I'm trying to understand how meaningful the comparison is between using that if it's only trained on matplotlib versus if there were a lot of other APIs, like how well would it do if there were a lot of other APIs and code examples.
I understand. So there may be a bias because Google is for general purpose information retrieval, but in our instantiation of the experiment condition, we attach matplotlib to every query we submit to Google. So in a sense, it's kind of limiting Google's search space to matplotlib too.
We have time for maybe one more question. Can you maybe talk a little bit more about the n-gram model? Because it seemed like you were taking a nested structure, as you were saying, which is code, and then flattening it, right?
Yes.
So can you talk about kind of the trade-offs that you were thinking about? Because a parameter that's deeper in the source code might be less important than something that was
yes, exactly. So there is actually a trade-off being made here, and the trade-off is that we prefer in this paper in the scope of this paper we prefer simply more simple model because this is still a kind of early work compared to later on what people might improve based upon this. So by using n-gram, we sort of sacrifice all the dependencies or the order information between the code elements. But this makes us, makes it available. I mean, makes it possible for us to train on rather quite a limited data set. So although we have 90,000 code examples, it's still kind of not that much. So we want to be able to develop a relatively simple model to deal with this situation.
Okay, thank you.
Thank you.
Let's thank Shiyan again. And